Welcome back. Today we are going to discuss about CMOS inverter analysis. As we know from various pull-up concept, complementary metal oxide semiconductor inverter configuration is the best inverter configuration. Once again, I'm just quickly recap what is a CMOS inverter structure. In CMOS inverter, if you observe that there are two transistors, one is a PMOS transistor and another one is an NMOS transistor. Is it clear? Where PMOS transistor will work as a pull-up transistor and NMOS transistor will work as a pull-down transistor. Therefore, it is known as a complementary metal oxide semiconductor. Now you can observe its operation when Vin is equals to 0, then this PMOS transistor is going to be turns on and the NMOS transistor is going to be turns off. Therefore, the output is going to be charged to VDD. If you consider the load capacitor here, okay, then this load capacitor will charge to VDD. Is it clear? Now you may observe very clearly when Vin is equals to 1, then this pull-up transistor will be turns off, this pull-down transistor will be turns on. If you consider the load capacitor here, then this load capacitor discharges towards VSS. Is it right? This is an operation. If you observe very carefully, when Vin is equals to 0, okay, you are getting an output as VDD, absolutely. Then similarly, when Vin is equals to 1, you are getting an output as VSS. Is it understood? Therefore, the transfer characteristics, if you observe the transfer characteristics or DC characteristics of this, if you consider V in as your input and V out as your output, then you may observe this is the transfer characteristics. Is it clear? But here it is an ideal case. If you look about the practical case, that means if you look very deeply the analysis of CMOS inverter, you can able to know what is the exact process present in that. Is it clear? Yeah, let's observe these transfer characteristics in various regions. Let us consider this is region number A, region number B, region number C, and region number D, and region number E. Okay, that means how many regions are there? 5 regions are there. Are you clear? Now you can observe very clearly in region number A, if you talk about this first region, what is happening to the output? The output is constantly, what is that? VDD. Therefore, in this region, I can say that only one transistor is in linear region, that means in active region. What is the transistor when V in is equals to 0, which produces V out as VDD? Absolutely, PMOS transistor. Therefore, you can observe that in region number A, only PMOS transistor is in active region and NMOS transistor, if you observe, it is in cutoff region. Is it clear? Now, similarly, if you talk about region number E here, okay, that is the fifth region. If you talk about the fifth region, what is an output if you consider 0? Is it clear? That is VSS. Then you can clearly say that which transistor is in active region? Absolutely, NMOS transistor is in active region. What about PMOS? Absolutely, it is in cutoff region. Therefore, you can observe in region number E, that is region number 5, PMOS transistor is in cutoff region and NMOS transistor is in active region. Is it understood? Okay, then if you talk about region number 2, observe very carefully what is happening in region number 2 here. That means region number B. Okay, the output from VDD to, it starts towards what? VSS. I hope that are you clear? It starts towards VSS. Therefore, we can say that it is approximately equals to VDD, but it is not exactly VDD. It starts decreasing. Therefore, we can say that NMOS transistor turns on. But we can't say that NMOS transistor is fully turns on. Therefore, we can say that in this region number B, if you observe very clearly, in region number B, if you observe very clearly, this PMOS is in active region. Is it understood? And the NMOS is in which region? Saturation region. I hope that are you getting the point. Why? Because here the curve starts to decrease. When it will start to decrease? Whenever pull down transistor is turns on, then it will start to decrease. But it is nearer to VDD. Therefore, we can say that in this region the pull down transistor is in saturation, but PMOS is in active. And exactly opposite here, if you observe this region, region number D, that is the fourth region, if you observe that exactly, it is not equals to 0, but it is approximately equals to 0. Therefore, you can say that NMOS transistor is in active. Is it clear? But it is not equals to 0. It is having some, output voltage. Therefore, you can say that PMOS transistor is in which region? Saturation region. Is it clear? Now, observe very carefully exactly in this region what is happening. That means you can say that in region number 3, what is happening? If you observe this region, any guesses from anybody? Absolutely. Is it clear? Why? Because in this region, if you observe that no transistor, okay, is in active region and no transistor is in cutoff region. Therefore, the two transistors are in which region? Saturation region. I hope that are you clear. If you observe this one, this belongs to region number A, B, C, D and E. These are the 5 regions of operation of the two transistors. If you observe, if you talk about its current graph, if you observe very carefully how the graph will looks like, okay, if you look like the current versus voltage, if you observe that in region number 1 and in region number 5 we do not have any current. Why? Because here only the PMOS transistor will be inactive, only NMOS transistor will be inactive. Okay, here the PMOS is in cutoff, here the NMOS is in cutoff. I hope that are you clear. If you observe in this region, exactly in this region, okay, a little bit of current is there. Why? Because here PMOS is in linear region but NMOS is in saturation region. I hope that are you clear. Okay, similarly in this region, that means in the 4th region, if you observe that, okay, in the 4th region, okay, in this region you can observe very clearly a little bit of current is there. There you can tell that NMOS is in active region, PMOS is in saturation region. Is it clear? Now you can observe in this region what is happening. There is a huge current. Why? Because both the transistors are in saturation region. That is a very important and a drawback of this CMOS inverter when you are going to analyze very practically in region number 3. That means okay, in this region there is a static current flow from VDD to VSS which leads to okay high power consumption and device is going to be damaged. Then what should we have to do? That is very important point. If you observe that very clearly, okay, if you draw a load line from here, then you can get a clear cut picture that V in is equals to what? V out. Okay, V in is equals to V out. Is it clear? Therefore, you can observe very clearly V in is equals to V out. Can anybody tell what is this value? Absolutely. If you observe the maximum value here and from here, it is exactly half. Is it clear? It is exactly half. You can observe very carefully. Is it clear, all of you? It is exactly half. Therefore, if you observe that, what is that voltage here means? Absolutely. It is half of the VDD. Is it clear? Therefore, if you maintain this V in as VDD by 2, then it is possible to overcome this saturation region concept. Why? Because high switching capability is going to be present. High switching capability. Is it clear, all of you? Okay, then we have to derive some expression here. Okay, IDS versus VDS. Is it clear? Therefore, the input voltage should be in which form? Absolutely, VDD by 2. If you maintain this V in as VDD by 2, then we can say that there is a fast switching from on to off and from off to on. Therefore, even though there is a static current flow, it can able to be negligible. It is negligible. Is it clear? Therefore, the major task is how we are going to obtain this V in as VDD by 2. Okay, that is a very important concept. Is it clear, all of you? Therefore, we will see this in the next class. Is it clear? Thank you very much. If you are having any doubts, you may ask.